Hello, everyone. Welcome to the SNEA Networking Storage Forums webinar on storage networking for virtualization, best practice considerations. This is an extremely popular topic. We've gotten a lot of people who are interested in this. And we're going to be talking, obviously, about the intersection between virtualization and storage networking. I'd like to welcome you to the webinar, and I'd like to welcome our guest speakers. My name is Jay Metz. I'm going to be your mostly silent moderator today. I'll be fielding your questions and feeding them off to our fantastic guest speakers. Jason Massae, did I pronounce your name correctly? I meant to ask earlier.
Yes, that's correct. Massae. Yes, that's correct.
All right. Having a weird name myself, I try to be cognizant of other people's pronunciations. He is going to be riding his ATV through the virtualization landscape, along with Cody Hosterman from Pure Storage, and together they are going to be introducing us to some aspects of networking and virtualization that are from the interest that we've been getting quite popular at the moment. So a little bit of administrivia before we get started, just to let you know that one of the things that could happen if you have a lot of tabs open in your browser, sometimes you might find that audio coming in through the browser might be choppy or difficult to hear. We have found that clearing out your cache might wind up being something that is useful for getting the audio to clear out properly. I also want to let you know that in advance, and if it sounds like I'm rushing, I am, because we've got so much material, I don't want to spend a lot of time here. But you need to know that you will be getting the opportunity to download these slides after the presentation. And we are going to solicit your questions and your comments. Obviously, we are presenting this as a vendor-neutral approach to doing the storage networking topics with virtualization, and we are sponsored by SNEA, the Storage Networking Industry Association. And to that end, just a quick bit of notice. Everything in this material is copyrighted by SNEA, otherwise noted. And you can use the material in presentations or literature as long as you don't change any of the slides. One of the things that you should probably be aware of is that we have lots of material that is available. We have an entire library of material open to you to be able to use. And we do wish to encourage you to do so. So, having said all of that, I am going to shut up real quickly. But actually, no, real quick. I want to point your attention to the question button on your BrightTalk interface in your browser, because if you do have any questions, I would like you to ask them. I want you to feel free to ask, and we will get to them as we can. We've got a lot of material to cover today, and any questions that we can't get to will be summarized in a Q&A blog that's posted usually about a week or two after the actual presentation itself. So come back and look at the SNEA NSF blog for the link to the Q&A session if you don't find your question answered, or if you wish to find additional descriptions and explanations on those answers. So without further ado, I'm going to pass this over to Jason and have him go through what the plan is for today.
Thanks, Jay. Excuse me. So as we go over this list, we're going to talk about some virtualization kind of in general, do a quick overview with that, and then we're going to go into some multipathing. Cody's going to dive into that area. I'll go over iSCSI, fiber channel, NFS. Cody will jump back into queuing. And the idea is to kind of cover some of the issues and best practices that we've seen both from different areas of the industry when it comes to virtualization and storage. Now, if you've noticed that picture of me on my quad, I kind of did that on purpose. There's a tow strap on the front of that. I do a lot of sand riding and go up on the mountains, and one of the things that I see is there's a lot of guys out there that will tune their quads for maximum speed. Well, I have made sure that my quad is maximum reliability, and because of that, I'm the one towing those guys with the fastest quads back down the hill and back to camp. Because what good is a fast environment if it's not reliable? So reliability is absolutely key, and that's the focus of this presentation. As we go through this, one of the things that we started talking, as I start to talk about this, is best practices and most common issues. Number one is iSCSI. Absolutely, without a doubt, we get continuous calls. There's always something, whether it's a networking issue, port binding, you know, how do I connect to my targets? iSCSI is number one. Second, and similarly, is FC. Same thing, configuring, zoning, a lot of times pathing may be incorrect. Next, maybe queuing. Maybe somebody's gone in and heard that they were supposed to do some queuing changes, or thought that they were supposed to modify something without talking to the vendor or looking at maybe a best practices article. And then next would be NAS or NFS. Typically that's on the networking side that has to do with that. It's usually not enough bandwidth, maybe they don't have their pathing set up correctly, or there's not enough throughput in the environment. So with all of those, we can end up with latency, connectivity problems, and as a result, we don't have a reliable environment.
All right, so yeah, thanks Jason and Jay. So let's talk a little bit about virtualization at first. Like, let's just level set here so you know we're all on the same page. And there are a variety of virtualization vendors, right? I mean, here's the common ones: VMware, Microsoft, KVM, Citrix, Red Hat, et cetera, right? They all have their differences, right? They have their settings and their features and this, that, and the other. But fundamentally, right, they're all the same idea, right? They're having multiple OSs run on the same physical hardware. They're abstracting, right, those resources, network, CPU, memory, storage, right, to provide a kind of a common interface to your applications and your operating systems, right? Removing that hard connection from whatever that OS is, whatever application's running inside of that OS, from the underlying physical resources, right? So you can do some cool things, right? Moving VMs or OSs non-disruptively across hosts, right, or across storage platforms, et cetera, et cetera. A lot of those traditional migration issues you had or traditional disaster recovery problems you had to solve are mitigated by this design, right? And so that's what all these vendors offer through their virtualization platform. So a common thing that happens, and this is kind of in many ways the basis of this entire presentation, is that every so often someone will say, hey, you know, I used to run my SQL server on a physical server and it was fine, and then you virtualized it and now it kind of sucks, right? The performance is not what it was. It's not getting the number of IOPS that I expected. It's having higher latency or everything, right? Why? What's going on here? Is the virtualization layer causing a problem? Does virtualization inherently cause performance issues? Is it inherently overhead? Right? In the early days, the answer was maybe, depends. It depends what you do, how this feature is enabled. In general, not really, right? Those traditional performance problems, the overheads that were maybe existed in the hypervisor 5, 10 years ago, don't really exist anymore. Those problems have been solved. But that doesn't mean you don't have performance issues. That doesn't mean by just moving an app, porting an app from physical to virtual, it's going to behave the same way, right? And there's a reason for this, right? Virtualization, by design, by definition, right, is about shared resources, right? It's about sharing resources to get better efficiency in your environment, right? Not every OS is going to use all the CPU, all the memory, all the network bandwidth on a physical server, so why not use that for another, or a 10 more, or 100 more? Right, and that's fundamentally what virtualization offers. But because of this, it's also designed for fairness. Right, it doesn't want a single application, a single operating system to necessarily go crazy. Right, no one should be able to use all the resources by default. So there needs to be a little bit of fairness there. Right, they want to make sure that things get their little chunk when they need it, and that not everyone can, not something that goes, some antivirus or something like that goes crazy and starves everyone else. So this is a fairly easy thing to control when it comes to CPU or memory, right? You give the VM 2 CPUs, right? And well, there you go. It's got that amount of CPU power. You give it 8 gigs of memory, 10 gigs, 6, whatever that is, and that's what it gets, right? And you can do some things like over provisioning and so forth, but it's fairly easy to tell how much CPU power is left on this host, how much memory capacity or whatever is available on this host. Right? It's a fairly easy thing to control. I mean, I know you can get into some crazy details with NUMA and all that type of stuff, but generally that concept is a little bit easier. But storage is not so straightforward, right? How is that controlled? Because just giving something 10 gigs doesn't necessarily correlate to performance, right? Just because you gave something 10 gigs, it could be doing 10 IOPS, or it could be doing 25 gigs a second, right, to those 10 gigs, right? How that gets divided and separated out is very different, right? And because when you look at the overview of how your hypervisor works from a storage perspective, right, is that it uses the same underlying design, right? You have some kind of storage platform. You likely have a switch or switches, right? And you have some kind of HBA or NIC or whatnot on that host accessing it. That part doesn't fundamentally change. Right? So from the storage administrator or the network administrator, things look similar, right? And so someone goes and complains about storage performance inside of your hypervisor or inside your VM running on top of it. Everyone's like, well, hey, nothing's changed here, right? So it's not our problem. There's something wrong inside of the hypervisor. And, I mean, it may or may not be true, but there are different considerations because of what we talked about before, because there are these different chunks, right? And who controls what part, what chunk, does also change a little bit in the hypervisor, right? Because the person that traditionally owned that, maybe your DBA, your OS admin, may not have that control anymore because of how hypervisors work. And let's take a look at this, right? Because VMs, you know, and I'm not the most greatest PowerPoint designer here, so forgive my squares and rudimentary lines, but hopefully it gets the point across. Right, is that these VMs are not just sharing the resources, sharing the CPU and the memory inside of that server. They're also sharing volume. Right, and what this volume is, this data volume, this LUN, this disk device, whatever you want to call it, right, can be presented in a variety of ways. Right, whether that's a array-controlled file system like NFS, something like that, or some kind of host-formatted block device. You know, leveraging FCOE or Fiber Channel or iSCSI or whatever, and then that end host puts a file system on it. So VMware with VMFS or Microsoft with NTFS and so forth and so on. And on that single volume, you then have multiple virtual machines, right? Multiple virtual machines with multiple virtual disks. And this is very different, right? Because essentially, I mean, storage arrays, NFS, whatever, were designed, I mean, you could argue about mainframe and virtualization, that kind of stuff all day, I guess, but they were out there really before your x86 virtualization as it exists today, for the most part. They were designed for physical servers. Here's a volume. Here's a configuration for that volume. That volume hosts my SQL database. It hosts this. It's a boot volume, whatever. And so that's the way arrays were designed. But virtualization turns this on its head, right? This volume now could host not only dozens, but hundreds, or I've even seen sometimes thousands of different applications, right, with different performance profiles. And so the considerations around this can change. And where you troubleshoot the problem, how you figure that out, is different. So that's really a key point, right, is what is the storage now for my VM? Well, as I said, we have some kind of clustered file system generally, right, that's presented to multiple physical servers. In this case, it's 32 terabytes. I just randomly picked it, right? It's usually large, right, because it's easier, one less thing to manage, just make it big. But that is subdivided into files, right? It's a file system, right? Files. Those files are generally large files, right? And what those large files are called virtual disks, right? And every hypervisor has their own name for it, but it's essentially a virtual disk. It's some kind of file system, whether it be NFS or VMFS or NTFS, and on that are files. And those files are presented up to those VMs as storage devices, right? And to that VM, they look like a local disk, right? They look like a local block device, regardless to the underlying infrastructure, whether it's NFS, whether it's VMFS, whether it's iSCSI, whether it's Fiber Channel. to that guest, they see a disk and it looks local, doesn't really matter what's below it. And the VMware administrator or the Microsoft administrator or the KVM administrator decides how much storage they get, and they subdivide it in those disks. And each VM can have many, many of them and present it up to that, right? And that's what the VMware administrator sees, right? And so the important thing is there's a couple layers here. There's not just the OS virtualization, but there also is storage virtualization going on here. And so understanding those different, understanding how they work, and understanding who to communicate with when there's an issue or a problem, right, is an important thing. And it's really probably one of the number one things that we really see when it comes to performance troubleshooting or configuration in a virtualized environment is communication, right? Knowing where to look, knowing who to talk to, right? And there are a variety of tools, of course, that make that easier, but our goal here is to say, all right, let's assume I have no tools, let's understand the stack. So the very basis of this is multipathing, right? Hey, I want to have more than one physical path to my storage, right? The storage is aggregated right from the compute, and so I want to make sure it's reliable, right? And of course, this doesn't really change. This is any different than a physical server or whatnot, right? The concepts all are the same, right? I want to make sure I have multiple redundant paths to my storage, right? Use more than one HBA, right? Use more than one NIC. Use more than one switch, right? Use multiple targets on that target array, right? You want to make sure that a single failure does not remove the access to your storage, right? Especially because a single failure, right? If you have all your hypervisors, right, attached, maybe that's 4 physical servers or something, or maybe many, many more attached to a single port or through a single switch, right? And you didn't actually make sure it's connected through multiple one, that small little failure of maybe a cable going down could take out not just those 4 hosts, could take out 400 applications, right? And so it is, of course, even more important to make sure these things are done right. So, as I said, since we're not really specifically talking about this vendor or that vendor, we're not going to give you the settings or the CLI commands to check and test this and the exact recommendation on what to do, right? Of course, reach out to your storage vendor, your hypervisor vendor, or whoever, right, on these specific recommendations. But let's take a look at some of the common options here. So fundamentally, you have multiple paths, right? And that's great. But just because you have multiple paths doesn't mean that your host is using those paths. Right? Many default configurations, it'll see the first path and it'll use that path until it goes away. Right? That's how things often used to work, and to a certain extent sometimes still do, depending on if you make some changes. And so having those additional paths to fail over is important, right? Critical, but it's not necessarily also optimal. Right? You want to make sure you're also using them at the same time. So there are common options like what's sometimes called fixed path, or most recently used, some Lua-based options. There's some kind of, generic round robins, or I'll just throw some IOs down this path, and I'll move the next one, I'll throw some IOs down it. But more modern operating systems and hypervisors have more intelligent pathing mechanisms because they realize not every path is equal, right? Also, really depending on the underlying storage platform, that can also dramatically change. Maybe you have an overloaded switch, maybe you have a bad cable, maybe things are not 100% equal on every path. And so using every path 100% equally 100% of the time is not the right methodology. And so this is one of the things that have changed recently, right? And VMware released a new multipathing algorithm recently that's smarter. Microsoft's had one for a while, and many others. At least queue depth, right? Checking the queues on the paths and using the right one. Latency optimized, which path has the lowest latency? Let's check every so often, and let's get rid of paths that are really bad. Right? And so looking into that multipathing and making sure those are set properly is extremely important. And the general recommendations for most storage vendors and hypervisors are to look at those smarter ones, right? Start leveraging the ones that do a little bit more work for you. So the key thing here is talk to your storage vendor about the recommendation. Talk to your applications, right? Because there are certain requirements around maybe possibly Microsoft failover clustering and how these things work. But generally, the smarter the algorithm, the one that uses the most paths most is best, right? So round robin, but if it uses it intelligently, that's even better, right? And the goal here really as well is to make sure these things are set by default. This really shouldn't be a day 2 operation, right? When you're provisioning new physical servers, when you're installing new hypervisors, whether that's manual or in an automated fashion, these should be built in to that process, right? Make sure, hey, this host always has this rule or this setting to make sure it's using this proper pathing algorithm. Right, and many modern hypervisors have ways of setting these defaults, or sometimes they even have specific defaults by talking to the vendor built into their hypervisor for that company or this one, so it's done by default. And so the onus is a little bit on you to make sure that, is that done, is it not, but just make sure that's there. So it really should be a day zero operation. Right? And if you build that into your deployment, into your automation, into your installation of your hypervisor, right, there's less things that can go wrong. And going back to what Jason said, reliability, right? A big part of reliability is repeatability, or doing things commonly across all the hosts. I don't know how many times we've seen some weird issue, and it's because this one host was missed somehow, right? And so automation in many ways here is your friend. So the last point I want to make here, right, is consistency, not just horizontally, right? Multipathing across the host, but also vertically, right? Things like with using iSCSI and MTU, right? You want to make sure these things are set consistently across the stack. And Jason's going to talk a little bit more about what that means. But across and down, consistency is great. It makes things much easier to troubleshoot. It makes things much easier to support. It makes things much easier to automate, right? Which is where many of us want to go. And so consistency is particularly important. And also understand that multipathing means different things depending on what protocol, what services you're using, right? Is it block, is it file, what type of block, right? And understanding those differences is important. And of course, Jason's going to talk more about that. Take it away.
So we're going to dive into iSCSI first, being the most common and biggest pain point generally in the virtualization and storage connectivity. And I'm going to try and convey all of the different details and aspects of how you should be looking at your iSCSI. Of course, number one is network. Cody talked a little bit about that. You know, we definitely want to isolate the traffic. That should, your iSCSI infrastructure should be, think of it as you're doing it like an FCE. You want to try and isolate it as much as possible, even to the point of, if you have the capabilities, giving it its own network. Because if you do that, that's going to give you much more performance and allows you to isolate that traffic. The other thing is port binding. And I'm going to go a little bit into that in the next slide, but port binding generally is the best practice for iSCSI, and there's some reasons for that. Load balancing. You'll hear us mention this a couple of times. This is really important that, you know, don't overload a destination or a source by trying to connect several different hosts and then have, you know, 400 or 500 machines hitting one target. So you want to make sure you've got multiple targets, multiple paths, and ensure that you can see all of those targets from all of the initiators that you got in your environment.
Hey, Jason?
Yes.
I hate to interrupt, but you somehow seem to have fallen into a hole. It's very hard to hear you. Did your headset drop off or something along those lines?
No. Can you hear me?
No, you may have to get a little closer to the microphone, I'm afraid.
I can't get any closer. Let me try something else. See if I can switch something here.
Oh, there you go.
That is much better.
Okay. Interesting.
Sorry to interrupt, my friend, but it was really hard to hear you.
Okay. Well, let's get back in there. Talked about the load balancing, redundancy. Again, same thing. We want to make sure that we've got redundant in every aspect. That has to do with all of your physical links, your NICs, and your targets. We want to make sure that we've got no single point of failure in that aspect. Initiators should be bound to an individual NIC, and I'll go into that in a little bit. Redundant interfaces. We want to make sure there's no single point of failure. Same thing with storage. Now, this first little line there, don't share LUNs outside the virtual environment. Surprisingly, we've seen this happen not frequently, but it's definitely worth mentioning. If you have a storage target, whether it's a LUN or a volume or anything like that, it should be dedicated to your virtual environment only. Do not share that with some other functionality. There is a caveat where maybe you're using, you know, an RDM or raw device mapping for a LUN, and that might be shared with, say, a clustering system. That's not what I'm talking about. I'm talking about you've got a LUN provisioned, you've got a data store in your virtual environment, and then you share that LUN out to some other functionality. What happens is there's different IOs going on there, and a lot of the vendors and the hypervisor will notice that and see that there's unknown IO happening on that target. And so then it has a really hard time trying to figure out what's going on, especially if there's algorithms for trying to balance across interfaces or across clusters. So make sure you don't share anything outside the virtual environment. The other thing is make sure that you provision, if you're not doing some of the newer technologies, like with LUNs and volumes, we want to make sure that you're provisioning the adequate resources that your virtual environment needs. So, you know, don't just think, oh, I can make this, you know, 50 terabyte data store and I'm just going to put everything on it, but you've only got, you know, 20 spindles behind it if it's all spinning media. You're going to crush that data store and you're going to have horrible performance. And it's not going to look like there's any performance going on the physical infrastructure, because it's going to look like everything's connecting, but you may see extreme IO load on the filer, and in the virtual environment, it just looks like everything's very slow. So you got to be really careful with that piece of it. The other option here is there's questions about NIC teaming versus port binding. The best practice is to use port binding, and the reason for that is that when you do port binding, not only do you have failover, but the SCSI initiatives are also looking at SCSI sense codes for the pathing. So if there's an issue down one path with port binding, SCSI initiatives can actually fail over a path and say, hey, that path isn't working. With NIC teaming, there's no SCSI sense codes that are monitored because it's just done on the physical layer. So port binding is definitely the best practices there. The other thing is, when you do port binding, you'll automatically get load balancing across all of the paths, because the filers and the virtual environment will initiate connections across every bound port. When you look at NIC teaming, there are some cases where some people want to do NIC teaming because maybe they've got a route and some hypervisors don't allow for that functionality. The other possibility is failover, maybe on a network level, because maybe the virtual environment doesn't support that. But this is where you really need to look into the hypervisor, make sure that that hypervisor supports port binding, and that is definitely the way that we want to get your infrastructure connected, is binding a port or a kernel to a physical device on your hypervisor. So now we'll get in here, and I'm going to talk about some of the different ways that this can be done. Sometimes you might route from one subnet or virtual environment to another storage target. That's one way of doing that. And then the other way is that maybe your virtual hosts and your storage targets are all in different subnets. In that case, you may need to do a separate gateway for each target. And so depending on the hypervisor, if they support that, that's something that you have to be aware of, and that you may have to put in a specific gateway for each target. And so those are things that you want to keep in mind when you're setting up this infrastructure. There are some that don't allow for routing, and so in that case, all of your environment must be in the same infrastructure. Now the next one, this is another one that comes up, is the different types of SCSI adapters or iSCSI adapters. Now, there's the software iSCSI, and there are some that believe that it may not have as much performance. And actually now with most of the hypervisors, the iSCSI performance is near line level. So that's not the case. The only thing you might gain if you were going to some type of hardware SCSI device is you're going to offload a little bit of the CPU processing. But the software iSCSI adapter will give you basically the same performance, at least at the storage level. One of the things that you do with iSCSI is that, of course, that's all software-based. So you're setting up a SCSI initiator, you're binding that initiator to a specific port. And one thing that I want to make sure that we understand is when you bind a port, there is no failover. It's an explicit bind, and it should not have another NIC that's a failover. So this is why it's very important that you have multiple interfaces, because let's say I had two software iSCSI kernels that I was binding. I would bind one to one NIC and one to the other. Remember, there is no failover that I want to do at a NIC level as far as setting up the NICs within the SCSI kernel. What I'm doing is I'm letting the SCSI sense codes and the initiators handle the load balancing and the failover. The next adapter type would be a dependent. And so that still has some activity. We still create a software SCSI kernel and then bind that to that physical adapter. That gives us a little bit of offload and allows the HBA to actually do some of the processing. And then next would be a independent. When you use an independent adapter, of course, there's no software kernel created. It's all done within the hardware itself. The key to the dependent and independent is that you would be using a physical device that is doing some SCSI processing. So you would need to make sure that you have redundant devices. In this case, with the dependent, I would create two kernels, two software kernels. And with the the independent, I would not create any kernels. With a software kernel, I only need to create one. There's really no reason to create more than one software SCSI kernel. Now, this is not the initiators. This is the kernel itself, and this is, might vary from some of the different vendors, but it's important to make sure that you understand which adapter you have and which one you're going to be using. Some of the other aspects that you want to think about is that you don't mix adapters. So you don't want to have, some software, some hardware. All of them should support IPv4 or 6. Like I said, software supports near line. Now, this is one that I really want to bring up. And Jay is pretty good about reminding people about this as well. Recommended is using jumbo frames. And you see I've got that big asterisk there. Only if your environment already has jumbo frames. If you do not have jumbo frames, do not go turn on jumbo frames. There's not a huge performance increase in the storage level. What this does is it will lower the CPU utilization a little bit, but the performance increase is pretty small, within a single digit of a percentage. So when we say recommend jumbo frames, it's if your environment and your network admin already has this running in your environment. So that's a really key piece there, because we get people that say, oh, it was recommended, and then they go in and they turn on jumbo frames, but they only turn it on in one point. Remember, when you do jumbo frames, every single device in that path has to support jumbo frames. And if you do it on one and not the other, then you're going to have connectivity problems and your reliability is going to go down. So, be very careful with jumbo frames. Next piece here is how many should you use? And this is where I talked about. When you have software iSCSI, you only need a single software iSCSI kernel. You can have multiple ports that you're binding for your initiators, but you only need one kernel. When you go into the dependent, that's when you're going to need multiple, right? Because now what we do is we've got the multiple NICs, and we're going to bind those to specific initiators, and we still have to have that kernel piece. Independent, of course, we don't have anything that is controlled by the hypervisor at all. Now I'm going to go into a couple of examples of setting up switches. This may vary from hypervisor to hypervisor. In some cases, we set up individual switches for each SCSI to physical adapter mapping. This makes it very simple, but it increases a little bit of the operational management. The other thing is that this allows, you want to make sure these are on the same subnet. Now, the other option, and this would be kind of a NIC teaming functionality, is that I'm using a single switch and I'm binding those to a pair. Now, with some of the newer versions of some of the hypervisors, they're now allowed to do a single switch independent binding, and this is where I was talking about that explicit failover. We don't set a failover from NIC 1 to NIC 2 for each SCSI connection, for each kernel. So VMK1 or SCSI kernel 1 is going to connect to NIC 1, and it will always only use NIC 1. If NIC 1 fails, then that kernel isn't used. It will fail over and use the other kernel. So that's one of the key pieces. Again, some of the newer hypervisors are starting to go down the iSER path, the iSCSI initiatives for RDMA. And so a lot of those do not support NIC teaming. So you have to be very careful if you're doing any of the iSER type of functionality. And this is, like I said, talking about that last one where you can use a single switch and bind those explicitly. Next piece is, again, make sure you work with the vendors on exactly how they want to do this, but it's that one-to-one mapping of an initiator to a port or a kernel to a port. And that way, when you're going to your targets, your initiators, you've got that redundant path, you've got those redundant connections, and you've got that redundant kernel piece that will fail over within the environment. The key is making sure if you're using dependent or iSER adapters, you must make sure that you're binding that kernel to those devices. The reason I bring this piece up is that maybe you've got a pair of NICs that don't support iSER, and if you were to bind that kernel to that unsupported RDMA NIC, then obviously that's not going to work. So in some instances, there may be, say, 4 NICs and 2 of them don't support RDMA. You just want to make sure you're very aware of which NIC you are binding that RDMA kernel to. Next, we're going to dive into fiber channel. Now, fiber channel, obviously.
Well, actually, before we do, we've got a couple of questions that are probably really salient to the section we just went through. If you don't mind, I'd like to try to hammer some of these out.
Sure.
We'll kind of work in reverse chronological order here with the most recent topic first. So with regards to the jumbo frames, a question has come in that asks about the mismatches in MTUs between the servers and switches, which it really is between different devices, but the question asks about servers and switches. Question is, will the highest MTU between the two get negotiated, or else will a mismatch persist?
So if you've got it set at the highest point and you have lower and the target and source match, then they will communicate. Right? So say you had jumbo frames at the switch level, but you were using, 1500 at a source and a target, they should still communicate. And Jay, you can correct me if you're wrong, being from Cisco on that piece of it.
No, you're right so far. I think I know where you're going with this.
Right. So the idea is generally what happens is somebody goes in and they go turn jumbo frames on the virtual environment, but then they don't turn it on the rest of the environment. And so the switch doesn't support jumbo frames or the target doesn't support jumbo frames, and that's where the mismatch can cause the connectivity issues.
Yeah, the way I see it, the way it typically I look at it is that if you're going through a series of hoops, at some point in time your ball will not fit in a hoop, and as soon as it doesn't fit in the hoop, it drops. So anytime you have a mismatch somewhere along the line, you always have a risk of having a larger frame not be able to go through one of the hoops and get dropped. And that can cause significant issues in other parts of the network as well. So you generally want to make sure that if you're going to be screwing around with jumbo frames, that it's an end-to-end solution with every single device in between having the same configuration settings. And I want to reiterate what Jason said earlier, which is if you're not already using jumbo frames, there's very little of reason to do so. If you're already using jumbo frames for specific applications, then that's fine because you probably already have your network settings set up. But you're not going to see much of a performance increase anyway from jumbo frames, and you're much more likely to have troubleshooting issues. So I just wanted to, kind of summarize for that part. I hope I didn't step on your toes too much.
No, that's exactly right. In fact, I literally just yesterday sat down with a customer, and this is exactly what had happened. They had turned jumbo frames on a kernel, but the network had no idea that they were using jumbo frames. So of course they couldn't do a vMotion because the hoop, like you said, the ball would not go through because it was too big.
Yeah. One of the things we also noticed too is that if you are crossing a layer 3 boundary with routers, one of the things that can happen is that the router MTU settings are almost always set to 1500. And so if for whatever reason you're crossing subnets or crossing a router, people will forget that the router itself will pin its own MTU settings onto a packet, even if all the switches are set correctly. So you always get unexpected things that go on. I'm going to hold off on the other question because I know we're running out of time. But thanks for at least addressing that question.
Yeah, I'll see if I can speed up here a little bit. We do have some stuff to go through. So fault tolerance, obviously we want to absolutely make sure if we have fault tolerance in all of our paths. Zoning is another one. We want to make sure you've got your zoning correct for your environment. Make sure that all hosts can reach the target for that virtual environment. Another thing is making sure your hardware, firmware, is current and supported. So sometimes you might have a newer version that goes on your HBA or your NIC, usually it's HBA, and, well, in this case it's HBA, and if it doesn't match or if it's not supported by that hypervisor, then you may have problems because they may have tested to say version 2.3.4 is what we support, but version 2.3.6 is available. So don't always assume that you go to the most current. The other thing is making sure you're consistent across all hosts. Every HBA should have the exact same version that you're using so that there's no issues with, a mismatch or a new way of handling some type of protocol. The other thing is, once you've provisioned an environment, it is highly recommended that you do not change any pathing policies. There can be some issues when you do this if the environment is in use and has already been provisioned. So if you do this, you'd be very, very careful. It's best that you remove everything from that data store because when you change a path, you may lose connectivity. So be aware of that piece of it. NFS, one of the big things here is do not mix NFS versions of the client connecting to a specific data store. You can usually mix versions within an environment, but not to a specific this volume. So that would say host 1 is using v3, host 2 is using 4.1 to the same target. That's what is usually unsupported, and that can cause a lot of problems because obviously they're very different. The other thing that a lot of people don't realize is that you can usually create a kernel or an interface that is dedicated to NFS traffic. That means you would go up and set up an IP that maybe is, the idea is that we don't want to have to route, right? We're trying to reduce as many hops as possible between our storage environment and our virtual environment. So if we create an interface on the same subnet as the filer, then we have no routing, and we want to minimize hops, and that will get better performance. If you do use 4.1, we want to make sure that you're using multipathing on that, because that 4.1 is optimized for that functionality. Some of the other pieces here, 10 gig obviously is recommended. That's kind of becoming the standard. A lot of filers are also recommending some type of lag or LACP port channel. That can give you better performance as well. Remember, more throughput gives you better performance and reduces the latency. So if you're connecting to your filer with not enough bandwidth, or maybe you're only dedicating one interface, which again would be unredundant, then you're going to have poor performance. See, the key to all this, as we talk about this, is making sure that you have the connectivity and the target performance that your virtual environment needs. And that can be changed, that changes throughout how many VMs you might provision, what type of VMs might be provisioned. Maybe you have something that's extreme IO, and you didn't have that in your environment before. So now all of a sudden you're having storage performance issues. And that may be because now that target doesn't have enough resources to supply all the IO or bandwidth that your environment now requires. So just keep that in mind. The other thing that's really important is ensuring that you have identical configs on all hosts. If there's differences here, this can also cause a big problem. All right, so let's get Cody into queuing.
All right, let's queue it up. Great stuff. So there's a couple things here, right, around queuing, and there's a couple different parts of the stack where this can happen. Now, there's differences across the protocols. There are differences across the different underlying storage arrays. What we're going to focus on in this section is really, at this point, is the hypervisor layer, right? What's going on from the HBA or the NIC or the or inside of the hypervisor or even the virtual machine, because that's where usually most of the questions come up and problems come up. The other places do present issues at times, but it varies so much between vendors and protocols. We're not going to focus on that today. So let's talk a little bit about higher up the stack in the virtualization layer around queuing and really what this means. So let's level set again here. What is a queue? What is a queue depth limit, right? It's essentially, a queue is a line, right? I mean, it's the standard British word is for a line, right? It's a queue. And that's what it is, right? And the queue depth limit is how wide that line can be, right? How many cars can go on that highway side by side, right? How many things can be allowed through at once? And there's a couple ways of looking at this. Look at it in a non-storage and non-technical way, because sometimes this helps. Right? If I go to a grocery store and I have one clerk or one checkout place, right? One customer can check out at a time, right? That queue depth limit is 1, right? So if there are 2 customers that want to check out, one of them has to wait. If I double the amount of clerks, the amount of registers or whatever, right, then I have a queue depth limit of 2. So 2 customers can currently check out at the same time, right? Neither of them has to wait. Neither of them are adding latency to their journey through that grocery store, right, back to the parking lot or wherever they might be going, right? So essentially what queuing is in queue depth limits is about concurrency, right? Is having a queue necessarily a bad thing? No, really what matters is how long it's waiting to get in that queue or get through the queue. Having a queue isn't necessarily the problem. So what does this mean in storage? What is this called, right? So a queue depth limit has many names, right? How many outstanding IOs are allowed through, how many concurrent threads, in-flight IOs, right? And this is generally, you've seen these names when you're using performance testing tools, right? How many outstanding IOs do I want to put in and so forth. And that's essentially what it is, right? How much do I want to try to force through this at once? So if we have a queue depth limit of 32, let's say, and that's a fairly common number for a hypervisor, right? That means that 32 IOs by that host or that path in the line or that part of the line in the storage stack allows 32 unacknowledged IOs to be sent through at once. Once 32 have gone through and none of those have yet been acknowledged, like by the storage acking it or whatnot, then the 33rd that gets sent has to wait until one of those previous ones has been acknowledged and completed. Right? So this is how many IOs can make it through that part of the stack. And that's a key part, is it's not, the entire stack doesn't have the same limit. There are different places where there could be a bottleneck. Right back to what Jay said earlier, there are different sizes of hoops in different parts depending on how your environment is created. So from a hypervisor layer, this is a little bit different, right? So you have your storage array queue depth limit, right? And that's very array specific, right? There's also things like buffer credits and so forth in the network, but I said we're not going to really get into that. We're going to focus on the bottom three parts here. There's your device or LUN or volume queue depth limit. Then there's also what your virtual machine is allowing through, right? And what can be allowed to a single virtual disk, right? Because these are now abstractions that didn't necessarily exist in a physical world, right? Because these things are pushed up the path. And so there are different limits, right, to control the fairness and balance of your environment. So back to the point I made earlier, right, is that hypervisor are designed for this fairness. And from a storage perspective, queuing, queued up limits, really more accurately, is how this is controlled. This is how this is balanced across the environment, right? Hypervisors realize that, hey, I have many VMs. My friends in my cluster probably also have many VMs. My friends in this cluster are sharing this data store. Right? These VMs on me, data store. I don't want these VMs to interfere with them. I don't necessarily want my VMs to interfere with that host's data store. Right? I don't want necessarily this data store to take more than its fair share on this HBA. Right? And so these things are throttled and controlled through these limits across the stack. And here's another key part, right, is that the OS, the storage, is virtualized, right? So the OS owner, the Windows or the Linux admin, doesn't have control of the full stack anymore. They don't control the settings below the virtual machine and between the switch, right? The physical server is no longer under their control. And so they have a smaller part of what they can control. So if they make a change, oh, they're like, oh, I got, 100,000 IOPS on my SQL server, and now it's a virtual machine. But, oh, you know what? I see this. My VM OS is set to a queue depth limit of 32. Well, I'll just bump that up to 128 and I'll be good. Well, that does open up their bottleneck, increase the size of their hoop, but there's still another hoop below them that's still set at 32 or whatever that happens to be. So the first thing really about this is, of course, the underlying layer, right? And this is the one thing I did want to mention is this is really the first thing you need to understand. What does the underlying storage platform support? Right? What kind of concurrency does it allow? Right? Because if you open up everything above it, but my storage array only allows X or Y in terms of queue depth limits on this front-end port or the entire array or a specific volume, right? How different arrays manage that changes. Everything above it doesn't really matter, right, too much. And making a change above it, not going to give you much performance if the very bottom of your stack. Right? And so this is certainly the first thing you want to think about and the first thing you want to understand. Right? As these queues can be sometimes set as on the per volume, per target, or the whole array, right? And so in the cases where there are these limits, parallelization often is the key. Maybe parallelizing the volumes, the targets, or potentially even the arrays, right? So this is really the first thing you want to make sure you understand, and the people or admins or applications above you also. So moving forward here, host tuning, right? So let's say this isn't a problem, right? If it is, host tuning is not going to make a difference. But if your underlying array can take a lot of concurrency, then host tuning is where you want to go to open these things up. And so your physical server has certain limits on its HBA, right? To say, or it's iSCSI, the NICs, it kind of depends on your environment, but fundamentally the same idea, right? Is they have certain limits that are set, and they can vary a little bit to vendor. This is an example from a VMware hypervisor, what the defaults are for different options, right? Software iSCSI, some different vendors around their default queue depth limits. Right? But the important thing is this is set at the hypervisor level, right? This is not in Windows. This is not in Linux. This is in Hyper-V. This is in ESX. This is in Xen Server. Right? So if you move up the stack, virtual machines have their own queues, right? How much concurrency can be pushed out of a virtual SCSI adapter, right, for a given VM? How much can be pushed at one time to a specific virtual disk? Right? Different hypervisor, different virtual SCSI adapters have different limits. Some don't even allow you to change it. Some do. Right? So if you're experiencing latency in the VM, but below that you're not seeing latency on the array in VMware or Hyper-V or whatever you're looking at, right? I bet you there's a bottleneck in that application. It could very well be, hey, IOs are waiting to get out of it. Right? And so that's where these things need to be checked as well. So it does actually add kind of an additional place to check that maybe didn't exist on a physical server. Hypervisors and the areas below them, with minor exceptions, don't really see the latency above them, right? And so understanding that just because there's not a problem down here doesn't mean that there isn't a problem somewhere, right? And someone will probably let you know. So simply changing something in the VM, like I mentioned before, isn't necessarily going to improve performance, right? You're just moving the bottleneck, right? In many ways, the goal is to get rid of a bottleneck. You just hopefully make it smaller and move it somewhere else, right? In this case, you're just simply moving the bottleneck below you, right? Just opening it in one place is not going to make a fundamental difference to your performance of a given application, right? It needs to be set through the stack, right? That vertical consistency is important. Just because if you add 4 lanes to your on-ramp to your highway, that doesn't mean you're going to get to work faster. You're just going to be waiting on that on-ramp. A lot more people are going to be next to one another, but you're not really changing your performance or latency on your work commute. So there's a kind of a simple equation to kind of figure out what you can do and so forth on figuring out what are my maximum IOPS. And it's something called Little's Law. It's fairly simple math, right? If something takes so much time and I can do so many of them at once, this is how much I can do in a certain period of time, right? Fairly basic math. And so we can take that once again and look at our grocery store analogy. Right? If a customer takes 1 minute to check out and I have one checkout counter, I can serve 60 customers an hour, right? My minute is my latency. My queue depth limit is 1. I can do, therefore, one at a time in serial fashion, 60 customers. If I double it like I did before, I can do customers in an hour, right? 120 IOPS or whatever that happens to be. So let's look at your average latency probably on like an all-flash array, right? Half a milliseconds. It's easier math. 1 second, 1,000 milliseconds. 1,000 milliseconds per, and with half a millisecond per I/O, that means you can do 2,000 IOPS with a queue depth limit of 1. If you have a queue depth limit of 96, that means you can do 192,000 IOPS, right? And maximum potential if all things are equivalent across the stack, right? So you don't necessarily need to max out your queue depth limits to do what your application needs. Most applications, and remember, this is per volume or per host per volume, really more accurately. Most don't need that kind of work. This is one of the reasons that hypervisors lower them, because they're generally not that intensive workloads. So do I need to change this stuff? Well, yes, if you see queuing, if you see IOs waiting somewhere in the stack and you want that to not happen, sometimes you do, right? Hey, I don't need this VM, it's just antivirus going crazy. I don't want it touching someone else, right? Then maybe you don't want to change it. Hosts introduce latency that you do not want to see. If you are not getting enough IOPS, right, because it turns out you're constrained by concurrency, then yes, you want to do. Right? But in the end, most customers don't need to do this. Very few of the customers I talk to in the end actually need to make this change. Right? Because most workloads are distributed across not only data stores, but more commonly hosts. Right? This VM is doing 10 IOPS, this one's doing 1,000, this one's doing 50. They're spread across hosts. They're nowhere close to overwhelming those queue depth limits. Right? And also, these days, lower latency is fairly common. Right? And the lower the latency, the less important how fat that queue is, right? Because those IOs are being filled or completed so quickly that they can do a lot more, right, in the same period of time, right? And so that allowed concurrency is less important. Okay, and then just the last point I want to make here, I know we're running out of time, is that remember, the reason for this is that hypervisors are designed to provide some fairness. So messing with that fairness, right, may not be what you want to do, right? Because everything eventually has a saturation point, right? And what happens when you hit the saturation point? What happens at 7:30 a.m. when that highway hits its maximum? It doesn't go from 60 miles an hour to 55. It goes 60 to 5 miles an hour. When you hit that saturation point, everyone is punished, right? And this is what happens, right? So think about when you're changing this, because whatever level you change it at, then everyone that goes to that level, that HBA, that data store, that switch, whatever, could possibly affect it if it gets saturated. And that's really the key. Think about these changes and where you can do it. Be controlled through QDEP limits, through QoS, array-based QoS, or performance balancing tools, right? And everyone has different flavors of that. So just if someone goes crazy, if someone goes abnormal, who should be punished, or how do you want to control that, right? And there are a variety of ways of doing that. And certainly talk to your hypervisor company or your storage vendor on your options. All right, Jay, finish it off.
All right. Well, unfortunately, given the time constraints, I'm not going to be able to get to the questions at this point, but we will get to them in the Q&A, and we certainly want to be able to give those questions their due. Just in general summary, a couple of things just to keep in mind. Ultimately, at the end of the day, the applications are the primary litmus test for what constitutes a successful storage networking choice. You want to always keep in mind that the applications are king, and they're going to be the ones that require the proper use of one particular storage protocol over another. You also want to be aware of the impact of where the I/O gets processed, if it's in the hypervisor or on the hardware, like the NIC or an HBA. And you also, for certain types of storages, particularly block storage, you want to keep in mind what the oversubscription and fan-in ratio requirements are. In Fiber Channel, they are application-specific, but they typically tend to be far lower than an NFS or an iSCSI relationship. And finally, it helps to know how the protocols work end-to-end, because you don't want to change those storage network settings arbitrarily on a host, because unexpected consequences can and will occur. Networks in particular are not end device specific, so you have to keep in mind that the rippling effect can cause a tremendous amount of issues from time to time. We do have a session resources. In fact, as a matter of fact, the actual presentation itself is available, and I will put this onto, if I can figure out how to do this. Oh, looks like I can't. I don't know where it went. There was a button that I could actually send a message, but I apparently, oh, here we go. Try this one. I am putting on the actual display announcement right now for when where you can go pick up copies of this. And don't forget that there are a bunch of other NSF webcasts that are coming up that do go into some details about some things that have additional relevance with regards to virtualization, but also just in general with storage networking. I do want to thank you very much for joining us. Please make sure that you hit the feedback button. We're very keen to understand what you liked, what you thought you wanted to know more about. If there's anything that we didn't get to that you would like to, you think it might be a good topic to pursue later on, please let us know. We do this pretty much for the feedback. To be honest, we like to know that what we did actually had an impact. So please give us your honest feedback. Don't forget that the Q&A will be posted to the SNIA NSF blog, and of course you can follow us on Twitter at SNIA NSF. So to all of you who joined us, and especially a thank you to Jason and Cody. Thank you so much for joining us and taking time out of your day to work with virtualization and storage networking. Thanks a lot, guys.